Hello everyone, thank you for tuning into my presentation on flexibility potential in local energy systems. My name is Anjali Wadhera and I'm a research officer with Natural Resources Canada's CanMet Energy Lab, and I will be sharing an overview on flexibility in the context of local energy systems, along with some considerations to keep in mind as we attend this virtual workshop. The traditional unidirectional power grid is being transformed, whether it's increasing variable generation penetration, new types of technologies and loads, or the uptake of electrification. Considering the graphic shown on the right, several different pathways have been formed and will continue to form, requiring bidirectional power flow and an interactive grid in order to transition to a modernized power system. Not only are decarbonization efforts influencing generation connected to the bulk grid, but distribution grids as well are seeing an influx of distributed generation. As we all know, these clean generation sources are variable by nature, like wind and solar, and do require types of storage in order to optimize their usage. Beyond traditional battery storage, there does exist potential within end loads across various sectors, from commercial to industrial and residential loads. So loads within these sectors can be considered untapped potential to support grid operation, reliability, resiliency, and optimized system utilization, which I'll be referring to as flexible loads. So I'll elaborate more on what shape and form these flexible loads take on as I continue in my presentation. But for the purposes of this presentation, I would like to discuss flexibility as a definition that's presented on the slide. So flexibility is the ability of a power system to cope with variability and uncertainty in both generation and demand while maintaining a satisfactory level of reliability at a reasonable cost over different time horizons. Let's now dive into the sources of grid flexibility. Sources of grid flexibility can span from traditional generation and bulk grid assets to loads and other storage devices. On the generation and bulk grid side, transmission capacity can be an enabler for the flexibility within grid interties. Generation sources like wind, solar, hydro, and natural gas also have flexibility potential with various enablers from regulatory to market structure to technical and appropriate incentives. On the load side, there are various different loads across different sectors, as I mentioned earlier. The residential sector uses demand response programs for peak shaving, but local energy markets leveraging ICT and market opportunities can be further exploited, especially if we consider aggregation using several smaller loads. The electrification of transport is a large area of research and deployment, with V2G and V2X concepts being explored. And larger EV adoption will result in several challenges for the grid, but there also exists opportunities to leverage these loads to act in V2G capacity to also support grid needs. Within the commercial sector, there's DR programs that are also enabling flexibility, as well as local energy markets that can further tap into flexibility that exists within commercial buildings like HVAC systems, for instance. And then similarly within the industrial sector, there are large massive processes where rate structures and DR programs can enable industrial plants to revisit their operations in considering providing grid flexibility if a business case can be made to do so. And then last but not least, we have traditional storage like pumped and hydro reservoirs that have flexibility potential and with cost reduction benefits in flow and solid state batteries, additional flexibility can be leveraged. Okay, so now that we've discussed sources of flexibility, let's review why we are interested in local energy systems for flexibility. The definition of a local energy system in itself is quite malleable in the sense that it can take on many different forms. So we can consider it to be a small street or neighborhood. It can expand to a larger campus or microgrid. We can consider it to be a feeder, or even a substation in some cases. So it's important to have this flexible idea of what a local energy system is with an arbitrary group of different loads. So given this context, local energy systems have a very diverse set of loads that are connected, each load having its own operation characteristics. So now this diversity can actually be a huge advantage if we consider the different types of flexibility that can be extracted based off of the operation of these flexible loads. So while we can use this flexibility for local contexts, local energy systems can actually also support bulk grid needs as well as serve as a resource in DSO operations, for instance. So to be a little more explicit, leveraging flexibility operation can, for one, accommodate better integration of new generation and storage options with types of generation, storage, and loads connected to the grid changing. So as renewable energy penetration increases, clean generation isn't always available when demand exists. So there are also additional complexities in integrating these variable generation sources on the grid. Then when you also consider the electrification of transport, for instance, this local flexibility can really be used to address these concerns. If we look beyond variable renewables that are supporting a cleaner grid, modernized grids will also need to provision grid services to balance generation and loads, in addition to supporting frequency and voltage to the same level of service that customers are currently experiencing, if not better. So local flexibility can serve as a way to operate local flexibility can serve these grid services like reliability, for instance. Flexibility can also provide the level of power quality desired by 21st century users. As technology changes and the way we live our daily lives, the services that customers want from the grid are also changing. So this flexibility can be another way for customers to find innovative ways to meet their objectives, reduce their electricity bills, or help contribute to clean energy targets. This could also be a way to motivate customers to become more active grid participants. With several flexible loads connected to the grid, leveraging this untapped potential would make better use of existing resources and potentially defer or reduce capital expenditure costs for grid operation, and also make better use of available capacity. Electric water heaters, for instance, have been used for several decades as a grid resource, but with the technology that's available these days, coordinating the flexibility from this one type of load is a lot more effective to support grid needs. And last but not least, flexibility can optimize grid assets and allow them to operate more efficiently. With access to more resources, if effectively integrated, this flexibility could maximize both ends of the opportunities and constraints when considering its flexibility potential. So this does offer additional flexibility to support bulk grid needs for a local resource to provide resiliency given the diverse set of loads as we discussed earlier. So it's worth noting that local energy system operation and flexibility potential, there's some clear-cut differences and similarities with bulk grid operation. So within local energy systems, the number of customers and the types of loads are drastically different, but the concept of using resources that are available and supporting a safe and reliable grid service, that concept is still the same. Okay, so now that we understand the role that flexibility can play in local energy systems and examples of what sources can provide this flexibility, it's important to understand how sources of flexibility can be characterized to identify the ideal source or sources to meet a particular grid need. With several types of loads across different sectors, flexibility potential varies significantly. For example, space heating in a residential context where occupants work during the day and come home in the evening would look drastically different than a commercial building's heating load where the space is occupied during the day and far quieter in the evening. So with this in mind, we kind of grouped up characterization parameters into two categories. The general category, there's very few parameters that are used to characterize flexibility, as the potential really changes from one scenario to another. So the proposed characterization parameters that remain static in this general category are capacities like energy and power, as well as the ramp rate. However, if you look into case-specific parameters, this list is a lot longer because of how much flexibility depends on these various different factors. So depending on the location of your flexible load, for instance, if you have an AC, flexibility will be very different in a cold climate versus a desert climate. If we consider user behavior and preferences, this needs to be considered to ensure occupants will continue to provide services. And if business operations or comfort constraints are interrupted or not met, it's possible that customers won't be happy with the level of service utilities providing and refuse provisioning these flexibility services moving forward. Time lag also refers to how long it takes for the equipment and controller to respond to grid signals, which is important when we're considering if we need a quick response or if we have a little more time to provision a service. So if you give the customer a 5-minute heads up versus a day or a week, for instance, the flexibility they might have available will change if they're able to precondition their flexible load, for instance. Then there's also other factors like response shape, communication infrastructure, device penetration, and predictability, which all play a role in determining the flexibility potential and whether a flexible load should be provisioned for a particular type of grid need. Okay, so lastly, as I wrap up this presentation, I wanted to leave you all with some opportunities and challenges for flexibility. So I'm not going to go through this list in too much detail, but just wanted to give some food for thought as you continue to reflect through this virtual workshop. So with various types of flexible loads across different sectors, something needs to be said for the power of aggregation. For several small loads grouped together, resulting in a lower margin of error for prediction and forecasting. However, if we deal with the line or transformer operation parameters like voltage limits, if not done correctly, aggregation can lead to other system issues that need to be considered. The valuation of service, I think, is a big piece of this puzzle. When we consider what operators are able to, or how operators are able to defer capital expenditures, this is a crucial parameter into considering how customers can be further incentivized and compensated for providing particular types of services. So there's also a consideration if we think about how these users have different assets and how to control these assets based off of ownership and who has rights over that device, as well as how these flexibility services can be procured. Other factors like communication infrastructure, regulatory barriers, economic factors, measurement and verification aspects are all factors that also need to be worked out if we want to be able to effectively integrate flexibility in local energy systems to support the modernized grid. So these are just a couple of references for those who are interested. But I would like to thank you for tuning into my presentation and look forward to interacting with all of you for the next part of the workshop. If you'd like to chat ahead of time or would like to reach out for further information, please feel free to contact me at the coordinates listed. Thank you very much for your time.